All right, so now let's talk about some of the physical properties of solids and liquids. Thank you. Before we sort of go on to talk about the physical properties of solids and liquids, they're all going to depend on what are called intermolecular forces. Okay, so let's just pick this word apart here. Intermolecular, meaning between molecules. So these are the forces between neighboring molecules. Right? So if I have one water over here and another water over here, these two molecules are talking to one another through intermolecular forces. And in particular, because we have that OH bond, these would be hydrogen bonds are the strongest intermolecular forces for water. Okay, but anyway, we need to rank these intermolecular forces. So the weakest are those dispersion forces. Okay, and again, those dispersion forces just arise anytime two molecules or atoms are touching one another. Slightly stronger than that are those dipole-dipole interactions that occur between polar molecules. And then slightly stronger than that are the hydrogen bonding that occurs when a molecule has one of these three types of bonds. Okay, it's actually also a dipole-dipole interaction, but it's a special type that's incredibly strong. Then there's a big jump, a big gap, and then we get to metallic bonding, that sea of electron bonds, electrostatic forces that occur in ionic bonding, and then finally the absolute strongest intermolecular forces are the covalent bonds in a network solid. Okay, so ranking these intermolecular forces by strength is going to be important as to for understanding properties of solids and liquids. Okay, so first of all, let's remember that we could transition from solid to liquid, right? And we know this just because we encounter it in our day-to-day life with ice mostly. If we take ice out of the fridge, or out of the freezer, it's a solid. If we let it sit to room temperature, it's a liquid. Okay. What's happening is that solid is actually absorbing energy, which is what leads it to be the liquid state. When we go this direction, we refer to this as melting. And when we go the other direction, we refer to it as freezing. In order to freeze a material to go from liquid to solid, you need to take energy away, right? So I add energy to a solid, it melts. If I take energy away, it will freeze. Okay, and each substance has its own, has a bunch of these, all these physical properties are going to be unique to this part, to whatever your substance is. Okay, so for example, boiling point. This is the boiling point of three different materials: diethyl ether, water, and mercury. And you can see how really what this graph is saying is that when you cross this line, that's the temperature at which your compound goes from being a liquid to a gas, the boiling point. Okay, so the higher the boiling point, the stronger the intermolecular forces. Right? And if you just think about it, you have these molecules that are all sort of touching one another, they're all interacting. If you want to get it to the gas phase, right? So this is now going from liquid to gas. You need to put in enough energy to break those intermolecular forces. Because like we talked about when we were talking about the difference between liquids and gases, gas molecules are very far apart, right? They'll expand to fit their container. So you have to put in energy in order to break up those forces. And so the stronger those forces are, the harder it is to break them. So let's look at these compounds here, sort of draw them out. Diethyl ether isn't one that you guys would know off the top of your head, so let me just give you the structure for that. here you have a water. Oh, you guys aren't going to know that. H3C, CH2O, CH2, CH3. All right, so it's a polar compound. So it's a covalent compound that is polar. And then on the other hand, we have water, which is a covalent compound that's polar, but it also has those special OH bonds. And then we have mercury, which is a metal. Okay, so let's see if we can't understand these trends in the boiling point that are being illustrated here based on what we've just written, right? So a covalent compound that's polar will experience dipole forces. Those are the strongest, so that's what we see for diethyl ether. For water, it has those dipole forces, but it also has those stronger hydrogen bonds. And then for mercury, it is a metal, so it has those metallic bonds. And so this makes sense because this follows this trend of what we saw over here, where dipole forces were weaker than hydrogen bonding forces, were way weaker than metallic bonding. And so that's why we see this trend in boiling point here, where diethyl ether boils at 34.6 degrees, whereas water boils at 100 degrees. And mercury doesn't boil until you get it up to 357 degrees. Okay, and so we can see this with, the trends in boiling point and melting point are the same. They all depend on those intermolecular forces, right? So here's a bunch of compounds, and they're being ranked by their melting point. So this is in order of increasing melting point. And we can see that the ones with the lowest melting point, all they have are these dispersion forces holding them together. When you have something that has not only dispersion forces, but also dipole forces, the melting point increases. And then when we have hydrogen bonding in there, so let me use a different color. When we have hydrogen bonding in there as well, now we get even higher boiling point, or melting points, as well as boiling points. Trends in melting point are the same as trends in boiling point. Then when we get to ionic compounds, notice we have this huge jump in the melting point. We go from being 103 to in the 600 to 900 range. Okay, and then to go even one more extreme, right? So what's the most extreme end of this here is not the ionic bonding, but these covalent bonds. Again, that would be something like a diamond is held together by covalent bonding. That has a boiling point, a melting point around 4,000 degrees Celsius. Right, so that's how much stronger those forces are in a diamond compared to an ionic compound, compared to a covalent compound that can hydrogen bond, compared to a covalent compound that can't hydrogen bond. It can only interact through dipole interactions. And then we have, whether it be a molecule or just a single atom, that are only interacting through dispersion forces, which have really low melting and boiling points. Okay, so now we're going to rank these three compounds in order of increasing melting point, only looking at their structures, so given no other information. Okay, so let's see if we can't classify these compounds a little bit further. We have lithium chloride, Cl2, so diatomic chlorine, and then what would be nitrogen trichloride. Okay, lithium chloride. If we go to our periodic table, what can we establish about lithium chloride? Well, lithium's on one side of the periodic table and chlorine's on the other side of the periodic table. So this would be an ionic compound, thus held together by ionic bonds. Chlorine gas is, this molecule here, Cl2. It's a covalent compound, but both of those are the same, so this would be non-polar, which means held together only by dispersion forces. And then NCl3, if we look at the periodic table, we have nitrogen here and chlorine there. So that's going to be a covalent compound. We're going to have to draw the Lewis structure in order to figure out whether it's polar or non-polar. All right, so I'm going to go through it quickly, but this is why that chapter 6 was so important. It's because it's going to bleed into this chapter. You're going to need to be able to draw Lewis structures in order to figure out this information. So here is the structure for nitrogen trichloride. Again, I have a lone pair on my central atom. That means that this is polar, but there are no nitrogen-hydrogen bonds, right? So I'm not quite at that level of hydrogen bonding yet. This is now just dipole interactions. So in order of the increasing melting point, the lowest melting point, the one that's going to be easiest is going to be this one, the nonpolar molecule held together only by dispersion forces. Chlorine, Cl2 is actually a gas at room temperature. The forces, intermolecular forces are so weak. The second highest melting point is going to be the nitrogen trichloride. I'm pretty sure that's a liquid at room temperature, held together by these dipole-dipole interactions. And then the strongest is going to be the ionic compound held together by those electrostatic or ionic bonds. Another property of liquids that we're going to talk about is viscosity. Okay, viscosity, the definition of viscosity is a liquid's resistance to flow. So how do we sort of encounter this in our day-to-day life? Viscous liquids tend to be very thick, think of like pancake syrup, and they also tend to be very sticky. Okay, so those are it doesn't have to be sticky, although that is a typical property of viscous liquids. But really it's that thickness, so think like molasses and honey. Those type of things are very viscous liquids. And it has everything to do with, again, those intermolecular forces. That's what this chapter is all going to be about, right? So higher viscosity means stronger intermolecular forces. It is important to note that viscosity is only a property of liquids. So solids don't have a viscosity associated with them, only liquids. So something would have to be a liquid before you could sort of compare or contrast its viscosity. But let's look at these two different molecules here. You can, this picture sort of illustrates that this one over here is the more viscous liquid. It's the thicker liquid and it's harder to pour. You can see based on how much is actually in that beaker, it's the one that's more resistant to flow. And these are very, very similar molecules. The difference is that this one has two of those hydrogen bonding groups, those OH groups, whereas the more viscous molecule has three of them, right? So this one is capable of stronger intermolecular forces. Move this over here so we don't get confused. And this one has the weaker intermolecular forces. Right? Because again, this is 2 hydrogen bonds compared to 3 hydrogen bonds. 3 hydrogen bonding regions, or 3 groups capable of hydrogen bonds. I just want to point out real quick, when I'm talking about hydrogen bonds, I'm not talking about this bond here. I'm talking about an intermolecular bond. And this is really what it would look like is if we have, let's say, one alcohol here, and then another neighboring alcohol here. These interactions would be a hydrogen bond. You have the hydrogen on one molecule talking to the oxygen of another molecule, and the hydrogen of that talking to the oxygen of the other one. Okay, so that's what I mean by hydrogen bonding. I'm not talking about this covalent bond here. I'm talking about a special intermolecular force. Another property of liquids, and again, this is unique just to liquids, is this idea of surface tension. Surface tension is molecules on the surface of a liquid that are sort of holding one another together. Okay, the easiest sort of I think the easiest way to understand this is to think of an example. If you take water, which is a compound that has a strong surface tension, and you put a drop of water onto a surface, it forms a bead type of structure, right? You get those little beaded up water things. If you did the same thing with, let's say, ethanol or isopropyl alcohol, any alcohol that you may have in your cupboard, you can kind of test this out, like the type of alcohol we use to clean wounds. You could test this out and take a dropper, and if you put a drop of ethanol on the table, it would form instead a really flat, kind of spread out type of droplet, right? Water has stronger surface tension compared to ethanol, which has weak surface tension. Okay, and that's just illustrated by those types of droplets that are formed. You may also, if you've ever, when you go out to the creek or to the lake or something like that, you have these bugs that are standing on the water surface, right? They kind of hop around on the surface of the water. It's not because they're floating, it's because they're actually standing on that surface and relying on water's strong surface tension to hold them up. Okay, much like our other properties we're talking about here, these are also dependent on intermolecular forces. Higher surface tension means stronger intermolecular, I'm running out of space. Higher surface tension means stronger intermolecular forces. Another physical property, and this is actually of both solids and liquids, is this idea of vapor pressure. Vapor pressure is the tendency of a substance to move from the either liquid or solid into the gas phase. Things that have really pungent smells tend to have high vapor pressures. Think of like nail polish remover or something like that, where you open the bottle, or like paint thinner, or even rubbing alcohol. When you open the bottle and you're immediately kind of hit, those are compounds that have high vapor pressure. These are actually sort of the opposite trend of what we've seen before, where the weaker the intermolecular forces are, the higher the vapor pressure. So high vapor pressure means weak intermolecular forces. Right, and take a second, take a step back and kind of convince yourself that that makes sense, right? If you have a compound that has very weak intermolecular forces, that means that the tendency for one of them to just sort of escape into the gas phase is that much higher because it's not really interacting strongly with its neighbors. Okay, substances that have high vapor pressures, we call them volatile substances. If something has a low vapor pressure, it's called non-volatile. So again, something like paint thinner or nail polish remover or rubbing alcohol, those would be volatile substances. Water is an example of a non-volatile substance. It has those strong hydrogen bonding interactions that prevent neighboring water molecules from escaping to the gas phase too easily. Vapor pressure also depends on temperature. Okay, so this is what this graph is illustrating here. Let's actually focus on one and then we'll look at the other one. This is a scale. On the x-axis is energy and on the y-axis is number of moles. And so this is at a given temperature. It doesn't really matter. Let's say 20 degrees Celsius. And you have a sample of, let's say, liquid water. The distribution of energy within that sample, you're going to see that a lot of molecules have these low energies here, and then as you get higher and higher in energy, you get to have fewer and fewer molecules that are at that high energy state, right? Well, there's this cutoff where if a molecule is higher than that amount of energy, it can actually break off and escape into the gas phase, right? So this is the point where you have high enough energy to escape to gas phase. All right. If we increase the temperature, what we do is change that distribution in such a way that we kind of shift it over to the right, right? So the blue curve represents the lower temperature. The red curve represents what happens when we raise the temperature. Now we have that many more molecules, the area under this curve right here, that have a high enough energy to escape to the gas phase, right? So raising temperature means you're raising vapor pressure. Okay, so these are the types of problems that we're going to encounter. Is given the structure of two molecules here, we want to figure out which one has a higher surface tension. Okay, so let me draw these out. This space here is weird. So let me just draw these out real quick. So this is CH3OH, and then this one is CH2OH, CH2OH. Okay, so which one has a higher surface tension? Let's actually make a little cheat sheet over here. Higher surface tension corresponds to what? Stronger or weaker intermolecular forces? This would be stronger intermolecular forces. Since this has one of these groups capable of hydrogen bonding, but the second molecule has two of those groups capable of hydrogen bonding, this one will have the stronger intermolecular forces and the higher surface tension. All right, and then just to review, which one would we think would have the higher boiling or melting point? Again, higher boiling point or melting point, bummer, corresponds to stronger intermolecular forces. All right, what's another one we talked about? Viscosity. Which one do we think will have a higher viscosity? Well, again, higher viscosity corresponds to stronger intermolecular forces. And then what about which one will have a higher vapor pressure? Remember, vapor pressure was the only one that kind of bucked that trend. The one that would have the higher vapor pressure is the one that would have the weaker intermolecular forces. Okay, so we would expect for that in terms of surface tension, boiling point or melting point, or viscosity, we would expect it to be this compound, that second compound. And then in terms of vapor pressure, we would expect it to be that first compound. And again, that's because the first compound has weaker intermolecular forces because it only has that one OH group. The other one has stronger intermolecular forces because it has two.